lesson in this chapter. So then we'll spend some time reviewing before we take the test. Yes. Okay, so we're talking about different proportions that occur in triangles, okay, and how to set them up. All right, so we learned previously that these two triangles are similar, right? If we look at this little one and we look at this big one, they're similar by angle, yes? Okay, because they both share this angle L, right? Okay, and since these are parallel, this angle here and this angle here are corresponding, right? So this triangle KLM and the big triangle JLN are similar to each other, right? Okay. All right, so we want to figure out a couple things here. We want to figure out LM and we want to figure out MN. So let's look at LM first, okay? And it tells us that LN is 16, okay? They give us that. All right, now, we can take and we can set up proportions because these triangles are similar, little to big, right? This little triangle has a side of 3. This big one has a side of 8, right? Okay, so I can take little triangle to big triangle, 3 to 8, and then I can go to the other side and say little to big. Okay, we've done this before, all right? And so we take 3 times 16, which is 48, equals 8x. Divide both sides by 8, and x is equal to 6. Okay? So LM is 6. Well, if LM is 6, can we find MN? What's it going to be? 10. Okay, because the whole thing is 16 minus 6 gives me 10. Okay, so that's what we've done already. Okay? But we have this thing called a side splitter theorem. Okay? And if we look at this, see how this side right here is parallel to the third side, this line here is parallel to the third side. Look at the relationship between these two sides. You have 3 to 5 and 6 to 10. What do we notice about those two fractions? 3/5 and 6/10. Are they the same? They are the same, right? Okay. So when you have this line here that's parallel to the third side, it breaks the two sides of the triangle into proportional parts. Okay. That's called the side splitter theorem. All right. It says if a line is parallel to one side of a triangle and intersects the other two sides, then it divides the sides proportionally. So I can set up a proportion, A is to AX, as B is to BX, okay? They did AM is to MB, as CN is to NB. They did it upside down than what I just said, but still basically the same thing, okay? But you can only do that when this line is parallel to this one, okay? That's when you can do that, is when that line is parallel to that one, then the two sides of the triangle are proportional parts. You can still do little to big. You can always do that if you know they're similar, but this is something else that you can do. All right. What is the value of x in triangle PQR? Okay, so we look at the triangle and we evaluate it. We see that we've got this parallel to that, right? Which tells us that these sides are proportional to each other, okay? So when I go to set it up, what am I going to do? Okay, so 12 over x plus 2 equals 9 over x. Good. And then we just have a proportion that we have to solve. So we end up with 12x equals 9x plus 18. And we solve for x, subtract 9x from both sides. And 12 minus 9 is 3x equals 18. Divide both sides by 3. And you get x equals 6. Something else that you might have is like they might do something like this. This is parallel, okay? And let's say this is x, this is 7. They might tell you this is 3 and this is 11. Something like that, okay? Well, I know I could set up a proportion, this is to that as this is to that, but what is this? Could I figure that out? If I know the whole thing is 11 and this is 3, this is what's left, yes? Okay, that would be 8. And then we could set our proportion up, okay? All right, I'm not going to mess with that one. It would probably work out crazy, but you could do something like that. Or the other, well, okay, mid-segment of a triangle, okay? And we talked about a mid-segment of a trapezoid back in chapter 6. Well, this is very similar. The mid-segment of a triangle is a segment of a triangle whose endpoints are midpoints of the two sides of the triangle, okay? So, this right here is a mid-segment, okay? Its two endpoints are midpoints of the two sides, okay? And so we have the triangle mid-segment theorem that says, if the segment joins the midpoints of two sides of the triangle, then the segment is parallel to the third side and half as long, okay? So, if this right here connects the midpoints of the two sides, it's parallel to the third side, and it's half the length of the third side. So if the third side is 20, then what would GH be? 10. Or if you knew GH was 10, then you could say that DF was 20, okay? So that mid-segment is half the length of the third side. All right. In the figure, XY, XZ are mid-segments. Okay, so this right here is a mid-segment, and that's a mid-segment, okay? Okay, so XZ, I want to find the length of XZ. Now, if this is a mid-segment, it connects the midpoints, and it's parallel to the third side. It's also what relationship to the third side? It's half. So if this is 13, then this is going to be 6.5. Good. Okay. Now we want to find ST. Well, it says that XY is a mid-segment, so it's parallel to ST. If XT is 7, then what do we know about ST? It's 14. Good. Okay. And so then the last one on here, it says find the measure of angle RYX. RYX. Okay, so we want this little guy right here. Now, remember that these are parallel to each other, right? This red line acts as a transversal, right? So if it acts as a transversal, what relationship does RYX have with 124? They're equal. Why? What kind of angles are they? Alternate interior. Remember, when you have parallel lines cut by a transversal, your alternate interior angles are equal, and that's what those are. So they're equal to each other. Okay, so that is 124 degrees. All right. Last thing. Well, this might be another, not last thing, I forgot. There's two more. Now, this is a corollary to the side splitter theorem because it works in a triangle, but it also works if you have just two lines that are cut by, two or more lines cut by transversals. If those lines are parallel to each other, it breaks the sides into proportional parts, just like it did in the triangle, okay? So we can do A is to AX as B is to BX. Those are proportional. And so there's a lot of different proportions that we can set up. Like we can do AB is to BC as DE is to EF. We can go back and forth. We can do AB is to DE as BC is to EF. And then the other thing we can do is we can take this little part, AB, is to the whole thing, AC, as this little part, DE, is to this whole part, DF. So there's a lot of things you can do when you have three parallel lines cut by two different transversals, okay? All right, so here's an example on how well you can see it on your paper. It says a reflecting pool is separated by walkways parallel to Lincoln Street and Jefferson Street, which are parallel to each other. Okay, so these are all parallel to each other. Okay. The city wants to add additional tiling around the pool. How much tiling does X feet represent? Okay, how much tiling does Y feet represent? Okay, so these are my two transversals right here, okay? And if these are all parallel, these transversals are broken up into proportional parts, okay? So what would I do to find X? I wouldn't cross. I don't know. Yeah, I would keep like here to here, or I could go directly across from each other. I don't know. I don't think I would cross like diagonally with it. I don't know. It might work, but I don't think I would.
I was gonna find the proportion and then.
Oh, you've already written the proportion in your head. Okay, well let's write the proportion for those people that are like one step behind. Okay, all right. So what would the proportion be? You could do that. X over 24 and 60 over 72. Okay. You could also do X over 60 and 24 over 72. You could do either one. Okay. So now, yes, we are going to cross. Okay. So we do 72X equals 24 times 60, which is 1440. Divide both sides by 72. So 1440 divided by 72, and X is going to be 20. Okay, so this would be 20 right there. Okay, now somebody else, Brian, help me out with this next one. What would I do to solve for Y? Remember, if these are all parallel and these are two transversals, these are broken up into proportional parts. Okay? What do you think? Any idea? No? Well, okay, if these parts are proportional, these have the same relationship as those, right? So could I do this over that? This over that? What do you think? I could, because they make the same fraction, right? If these are all parallel by the two different transversals, pretend like this one's not here, okay? These are going to make the same fraction as those are. That's what it means to be proportional, okay? So I could do 60 over 24 and then 72 over Y. I could go across to 60 over 72 and 24 over Y. I could do it like that too, okay? All right, so we're going to cross multiply 24 times 72, 1728, and then divide by 60, and I get Y equals 28.8. All right, so if these are all parallel, cut by two different transversals, then these are broken up into fractions that are the same. So this is to that as this is to that, okay? Or I could go 20 is to 24 as 60 is to 72. I could go across from each other also and set my proportion up. Okay, here's the last thing. If a ray bisects an angle of a triangle, then it divides the opposite sides into two segments that are proportional to the other two sides. Okay, so this is what happens, okay? And people make a mistake right here all the time. If this is an angle bisector, you remember what it means to be an angle bisector? Okay, it breaks the angle into equal parts. Does not necessarily break the opposite side into equal parts, but it does break the opposite side into a ratio that's the same as the other two sides, okay? So what I could do is I could say that UX is to WX as UV is to 8, okay? Because if I set it up like that, that's 12 is to 16 as 6 is to 8. Well, if I reduce both of those, they both become 3/4, don't they? Okay? So I could set it up like that, okay? The other thing I could do is this breaks, this goes it goes through the middle of the angle, but not necessarily the middle of the opposite side. but I could set up a proportion where I did XU is to VU as XW is to VW. So I could do 12 is to 6 as 16 is to 8. I could do it like that too. So basically you marry it up with what it's next to. Okay, so 12 is to 6 as 16 is to 8. Okay, so you could go left, right, or left, 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 or left, left, right, right. Sorry. Okay, all right. Okay, so let's look at this problem right here. Okay, so this right here is an angle bisector, right? It breaks the opposite side into a ratio that's the same as the other two sides. Now the problem here, and there's going to be some like this out there, this is x, the whole thing is 13. How do we represent this part? If this is x, and this whole thing is 13, this is what's left. When you have something that's left, what do? Subtract. Right? If this is x, the whole thing is 13, this is 13 minus x, right? Okay? All right. So this is my angle bisector. And so now I can set up my proportion. All right? So I can take x and marry it up with 10. So x is to 10. Maybe you stay on your own side. Stay right with the one that's next to it, and you'll be good. And then 13 minus x is to 16. Okay? So x is to 10. 13 minus x is to 16. And then you just cross multiply. You end up with 16x equals 130 minus 10x. I distributed there. Add 10x to both sides. So that's 26x equals 130. 130 divided by 26 goes 5 times. Okay, so if this is an angle bisector, it breaks this into a ratio that's the same as that one. So x is to 10, 13x is to 16. All right, last one. Okay, what is the value of x? All right, here we've got this angle bisector again. Okay, we got this angle bisector. It breaks this opposite side into a ratio that's the same as the other two sides. So what do you think? How could I set this up?
Did you say we could do, that was my English. Did you say that you could do left to left?
Yeah. Left to left like this, or left to right?
Left. You said.
I said left to left. Like if I start on the left side, I'm going to marry it up with the one on the left. Okay. And if I start with the one on the right, I'm going to marry it up with the one on the right. To me, that's the easiest way. But you can also go left, right, left, right. You can do it either way.
You do it that way?
You can. Yes. Okay.
That's the way that I did it.
Okay.
There was a number on. Like,
yeah, because this is going to be the same ratio as that. Okay, you can do it like that, or this is going to be the same ratio as that. Either way, it doesn't matter. Okay, Regan, what do you want to do? Left to right. Okay, so we're going to do 3x minus 7 is to 12. Right, left to right, and then left to right. 3x plus 3 is to 18. Got some big old numbers there, don't I? Okay, so 18 times 3 is what, 56? 16, 24. Yeah, you're right, 54. X minus 18 times 7, 126 minus 126 equals 12 times 3 is 36x. 12 times 3 is plus 36. So 54 minus 36 is 18x. Add 126 to both sides. 126 plus 36 is 162 divided by 18, and so x is 9.
I just always like to have one whole number.
Yeah. Okay, so we learned 3 things. We learned the side splitter theorem, right? If this right here is parallel to that, then it breaks the sides into proportional parts. A is to AX as B is to BX, right? Okay. Triangle midsegment theorem, it connects the midpoints, right? And this is half of that, and this is parallel to that. So if this right here was 6, what would DF be? 12. Okay? And then we said that if this is an angle bisector, it bisects the angle, but it doesn't necessarily bisect the opposite side, only if it's isosceles. Okay? So it doesn't bisect the opposite side, but it breaks it into a ratio that's the same as the other two sides. Okay? Left to right, or left to left, right to right. However you want to do it. Okay? All right? Okay.